Okay, hi everyone. Today we'll be discussing the paper titled Go Explore. So this paper is to solve problems that are called the hard exploration problems, okay, whereby the reward is very sparse in the environment. What this means is that it will take a lot of different actions in order for an agent to get even a single reward. And this is something that is difficult for reinforcement learning agents, because reinforcement learning agents typically learn by the reward. So imagine if you are an agent and then you receive nothing for doing like 10 different actions. So maybe there's only one sequence of a very specific sequence of 100 actions for you to get that one reward. You might take forever before you get that reward. But because the reinforcement learning agents, we tend to maximize the reward. We try to go towards the place with the highest rewards. There's no way to like exactly get the right signal in order to head to the right direction. And as a result, most agents do not solve this kind of hard exploration problems well. Okay, so today we'll be talking about this method called Go Explore, which proposes a way that could potentially solve such a long and tedious exploration process to discover a reward. So yeah, let's just take this by Uber Technologies, quite interesting. And so let's take a look at the paper. So this is the background. So there's this few of reinforcement learning environments called the Atari games. And in Atari games, there are difficult games. The one of the more difficult ones that the AI algorithms have not been able to tackle is this game called Montezuma's Revenge, where you control an adventurer and you're trying to find like the treasure room in the series of like rooms. So each room there's some obstacles that you need to avoid. And you see Go Explore performs very well. Over here, it passed like the human baseline. Okay, actually the human high score is 12 million. Okay, this one is slightly lower, but actually if they did without any restrictions, yeah, hold on. If actually they did the algorithm without any restrictions, you will realize that actually the Go Explore algorithm can actually surpass the human high score of 1.2 million. Okay, but this is with restrictions like sticky actions and so on. Okay, but even so, you can see that the next best random network distillation, and then like and so on, like DDQN, like even stuff like mu0 is somewhere here, mu0. You can see that there's a huge gap between this Go Explore and the next best method in reinforcement learning. And so the question we want to ask ourselves is, why do traditional reinforcement learning algorithms perform so badly at this kind of environment? And what special sauce does this Go Explore algorithm have that can enable it to perform so well? Okay, so because not everyone here knows what the Montezuma's Revenge is, let's take a quick view of how the game looks like. Okay, let me just share my my YouTube video. Hang on. Okay, so let's take a look at the Montezuma's Revenge. Okay, so this is a quick snippet of how it looks like, the game, just for your understanding. Okay, I hope that was an interesting video. I mean, if anything, the video was meant to show off how good this algorithm is. But one thing I didn't quite like about the video is that they suddenly like transition into the words and the gameplay. So if anything, maybe researchers can make better videos. but that was quite entertaining. You can see that the goal is like for the agent to collect some keys and then use the keys to unlock some doors. And then at the end, you get some like treasure room where you get the points. I myself never played this game before, but it does look quite difficult because you see when you collect the key, the score actually doesn't really change. Okay, I'm not too sure whether the score actually changes or not, but it is basically when you get a key, you do not get an immediate reward of solving the environment. You actually need to like go and open the door, collect the treasure and so on, which can be a couple of rooms away. So you also need to sort of like memorize the layout of the map because there's no mini grid here or anything. So that's the difficulty of this game. Okay, but humans can actually play this pretty well. Okay, but why can't algorithms search this space well? So let's take a look. Okay, so what has been done for traditional algorithms is that just purely based on the environment rewards, not enough to make the agent want to explore enough of the search space. Okay, because it might narrowly go towards like those very immediate rewards. Like maybe if you get the key, you get 100 points. Okay, then you just get the key and then that's it. Then the agent will be lost around there because the agent will not be able to find out where else to go to unlock the door because it might be several rooms away. Okay, so it is very similar to like when you're doing something or you pick up a key from the floor. Okay, like you walk outside, you pick up a key on the floor. You wonder where this key can open, which door can this key open. But there's so many doors for you to choose from. So it is very difficult for you to understand like if you're the agent and you have no context, you don't know where the key goes to. But for humans, I believe when you play this game, the key actually matches the color of the door. So there's some context here. But if you are the AI, you may not know where it unlocks it, and you may not even have found out where to unlock it. So there are some approaches called the intrinsic motivation approaches that have been done on this game previously. And what they have done is that they have incorporated some form of curiosity or novelty seeking so that you can actually prioritize states that you have never visited before. And because you prioritize states you never visit before, you actually, let's say you are at this state, you can actually prioritize states that you never visit before. You can actually move like and explore more and more of the state space because you never visit all this space before and then you get more interested in it. But for those states that you have visited before, you will prioritize them less. Yeah, so this is some form of exploration where you prioritize new states or you be curious and try to explore the environment to try to break out of the stalemate that current RL algorithms are facing. So intrinsic motivation did help to solve the environment a bit. Okay, I mean, with it, you can achieve level 1 for one of the algorithms. Okay, but there's an issue over here. Okay, so the issue is that if you use intrinsic rewards like this curiosity-based rewards, whenever you encounter a new state, great, it will encourage exploration of that state. But what happens after you explore that state? Then it becomes a scene state, right? So when it becomes a scene state, what will happen is that when you next encounter this state again, you are no longer as excited to visit there anymore. Okay, but the thing is, you might not have explored fully. There might be some state over here that you want to go to, but you have not explored yet, and this may be the goal state. But because of your intrinsic motivation, you see this as a scene state, then you think that, okay, maybe I won't go there again. I'll visit somewhere else instead. So you can see that with this, even with this intrinsic motivation based on curiosity, if the game trajectory is long enough, you may not visit all the states until the goal state at one go. And then your intrinsic reward will get lower and lower for this curiosity base. Okay, I'm actually doing research on this. The intrinsic reward I'm using doesn't diminish. Okay, so that one I'll share with you all more at the end of it. Okay, then 2 weeks later, we'll discuss more of my research, okay, on this intrinsic motivation, a new kind of intrinsic motivation. But based on the current intrinsic motivation, we are only doing this kind of novelty seeking, and then these rewards tend to go down over time because the state is no longer new. You will not be incentivized to explore anymore. It is actually very similar to like maybe like a baby when they actually figure out a new take a new toy, then like, oh, how does this work? Then after you figure out how it works, the baby doesn't really explore the toy anymore, right? Oh, by the way, can you all hear me speaking? I forgot to check just now. Is my voice okay? All right. So there's actually a problem with this kind of curiosity, novelty seeking rewards. I mean, it sounds very psychology in nature. Okay, but this problem, and this is a problem that I think myself that will be to happen, is that in real humans, actually, we may be curious, but we don't exactly explore all unseen states, right? So, okay, take for example, you are trying to play with a toy, okay, a new toy, and then maybe this toy, okay, is a combination number here, okay, and the number is like 0, 0, 0 something. You need to guess a 3-digit number. Then you need to roll the lock combination. Okay, how many of you here would think that as a human baby, you will sit down at the lock and go through all 1,000 possible all 1,000 possible states the very time I pass you a lock? Who here thinks that a human kid will go through all 1,000 states because he's curious to find out what number opens the lock? Raise your hand if you think that a baby would do that. Okay, who here thinks that if you give someone a lock, they won't explore all 1,000 states? Raise your hand. Take no response. Okay, so are you of the camp that when you give someone like this problem where you unlock a lock, a combination lock, do humans explore all the states? I mean, yes or no? I mean, just get some feedback. No. Okay, Goku said no. How about the rest? Randomly. Jet said randomly. All right. So actually, there's some merit in that. Okay, because sometimes there's just so many states you want to explore, but then it's so boring to explore all these states because it's like it's just a tiny tweak. You don't really get much joy from getting it. So just seeking novel states, okay, may not be the right approach to do it. Okay, we might want to seek, like maybe you just want to try, oh, it turns. Then after you turn a bit, you like, okay, it's just too tedious to get everything. I will just stop here. So actually humans, we have like a stop measure to just tell you like, okay, maybe this is not the way to go. Maybe I need to find a smarter approach and maybe look for clues to try to open this lock. Okay, but if you were to put this in an AI, the AI will explore all 1,000 states for you because it's very curious about every single state. So the way we denote a state matters. Okay, but I'm not going to argue too much about all this. Okay, this is my own idea. Okay, but based on this paper, the paper is just saying that if you use this kind of novelty-seeking rewards, you may not get the right way to solve a very long problem because these rewards diminish over time. So let us see, okay, in greater clarity, what this actually is. Okay, so we look at the diagram. So this is one of the problems with the traditional agents. Okay, they gave 2 problems, and the first problem is called detachment. Okay, what is detachment? A detachment means that if you have this kind of intrinsic reward or intrinsic motivations, okay, they may not discover the previously searched frontiers. And this is what it really means. Okay, suppose you have a maze like this. You can go left or right, west or eastbound. And this green is the fresh intrinsic reward that you can get because it's new to you. Very nice. So you go here, you explore this purple part here. But then because the episode ends over here, you don't explore fully. Okay, you're left with this green part here. On the second playthrough, you explore explore all this here. And then on the next playthrough, okay, you look on the next playthrough, you only explore like maybe here. Okay, you do not really go and seek out this great area here that you can potentially go to. Okay, why? Okay, because in order to reach this state here with all the nice rewards, you need to go through all these earlier states here. Okay, which if you had already taken the previous novelty reward, is no longer new anymore. So you may not want to go and explore there, and as such, you might miss out this rich reward area over here. So it would be great if we could somehow go here and explore this area. Okay, but because of the way, like even you use intrinsic motivation to reward your agents to try to explore new states, with the problem of the intrinsic reward being used up, okay, this might be something that you will suffer from. Okay, but of course, if you use intrinsic rewards that forever don't get used up, then it won't be the case. Okay, but for novelty is a reward that will be used up. So for that particular intrinsic reward, there's a problem. Okay, and for Montezuma's revenge, a lot of papers are using curiosity-based learning, which means that this is a problem. Okay, so what's the second problem that the paper identified? The second problem is called derailment. Okay, derailment is when you have identified a good state and you want to go back to that good state. But unfortunately, you are unable to go back to that state because of your exploration policies. So I think for people in RL, like maybe Jet, okay, you all will know that in RL, we always talk about explore, exploit. So in every algorithm that we do, it's quite common that there was an exploration component as well. Okay, and this exploration component, I'm just giving some examples here of some of the algorithms that have exploration components. Actually, most RL algorithms have exploration components, maybe except decision transformers, because that one is just a prediction, it's not an exploration. So, for example, epsilon greedy used in DQN, DQ networks. So what epsilon greedy is a behavior policy trying to make for every time you select epsilon, you select a random action. Every time you select 1 minus epsilon, you take the greedy action. So this kind of DQN, okay, even if you find a nice state, okay, there's also a small chance, okay, because of this epsilon parameter, you will take an exploratory action. Which means that if you want to, like, for example, at this start state, I'm just drawing a diagram for a start state here. You want to go to an intermediate goal state, or maybe we call it an intermediate state. Unfortunately, because of the way of the exploration, you cannot go to this intermediate state. You will derail off halfway here, okay, because of exploration. So unfortunately, no matter how you want to go back to this intermediate state, the exploratory part of the algorithm cause your algorithm to deviate from where you want to go to, making it hard to return. Okay, this is Monte Carlo tree search. This is called the upper confidence bounds in trees. Actually, the one that is used in Monte Carlo tree search is UCT, but it is based on this upper confidence bound where you actually have this is the value, which is the exploits component, and the other one is the explore component, where you basically explore states that are not chosen much. So you have an exploratory component here. And sometimes because of this exploratory component, okay, you are same thing, you are unable to return to a goal state, because when you do exploit through your game tree, you may not actually go to where you want to, because you need to cater for exploration as well. Okay, so you might ask, what about non-discrete state spaces, like if you use policy-based methods for reinforcement learning? So I use one of the famous algorithms called PPO, Proximal Policy Optimization. And over here, you can see that this is like the policy gradient. Okay, this is the actor. This is the value, learning the value for the, sorry, I think this is the critic and this is the actor. Yeah. Then this is the entropy loss. Okay, and this is what I want to highlight. So this entropy loss equals to tries to explore all actions equally. Okay, because the entropy loss is lowest when you explore all the actions with equal probability. So because of this, again, you have this problem where you have from the start state, you want to go to the intermediate state, but because of your exploration policy, you derail off, and then you are unable to reach that state. Okay, so these are the problems. Any questions so far for what I've described? Okay. Yeah, you understand this one? Okay, that's great. All right, let's move on. So let me illustrate the example using a torchlight. Okay, this was also done in their paper. I quite like this analogy. So this torchlight analogy is like this. Suppose you have a start state, okay, and you have a goal state, the S and the G. So if we were to explore from the starting state, I can do like a random exploration. It's like doing a random walk. So you end up with a list of states, like maybe a circle around your start state, okay, based on your trajectory, based on the number of time steps. This circle can be quite small or quite large compared to the actual game state. So in easy problems, okay, this random exploration, the circle would already have covered the goal state. Okay, but for example, in Montezuma's Revenge, it can be very, very far away from the goal state. Okay, so what we really want to do is we want to pick one of the points on the border over here. Oops, we want to pick one of the points on the border, and then we want to explore further from there. Okay, but because of the earlier two problems we saw, the detachment and the derailment, okay, it can be hard to explore further from this boundary. So most of the traditional RL algorithms, they are stuck exploring from the start state. They're unable to explore some more, and then they fail to reach the goal state. Okay, so end up they only search this circle. So the torchlight is only that bright. It doesn't search more than that. So the torchlight is unable to light up the entire map. Okay, but what if we have some repeaters? Okay, back to the engineering side. Okay, so how do we ensure that we can have this kind of like repeaters where we can like continue to shine the torchlight all around the house, all around the map? And that is when you have a next state here that you identify. Okay, and then instead of starting from this point, your start point is now here. Then you search. Okay, then you identify a nice frontier, next one, and then you search the next one. And then you identify a nice frontier, and then you search. And then identify a nice frontier, and then you search. Then eventually, you end up with the goal, and then you can connect one path from start to the end. So essentially, Go Explore is like this expanding torchlights. You don't only have one torchlight from the start, you have multiple torchlights, and then eventually you will light up a path from the start all the way to the goal state. Okay, so this is actually quite beautiful, and it's actually a wonder why reinforcement learning algorithms, we don't do such a thing. Okay, we are very stuck in this idea of explore, exploit from the start state. Okay, why don't we explore everything like that? So there's another thing that that could be used to like force people to explore out of this sphere. Okay, this is called count-based exploration, where basically you, based on the number of times you visit each cell, then after that you might not focus on the inner cells anymore. You might just focus on the outer cells. Okay, but even if you use count-based exploration, you may not be as quick to go to the frontier as it is from here. Okay, but one thing I don't quite like about this frontier method, which you will see later, is that you have to take some assumptions. You need to be able to sort of teleport to the frontier. Okay, so let's move on. So how do we explore mid-game? Okay, this is a very important question. So I would like to bring you to the analogy of a memory card. So anyone here played PlayStation before? I don't know if you're in the era or Game Boy. Basically, any game that have a very long gameplay, like an RPG game, you have some safe states. Then you can actually load the game from those states, right? Like a memory card. So how do we explore from like the frontier halfway and then like continue from there? It is very similar to like a memory card. You save the frontier, you save the game state, and then you load from there. Okay, and then you explore from there. So how do we implement this? So we implement it using this explore phase over here, where you take something from your memory, go to that memory, explore from there, and then update your memory with all the new states. And then there's also a second part called Robustify, where you perform some form of imitation learning or curriculum learning on the best trajectory using a neural network. So this first part doesn't need a neural network. I repeat, the first part doesn't need a neural network. So actually, if you are able to make your state small enough, you don't need a neural network to do this first part. And it's hard to do it with a neural network also, because if you do it with a neural network, you can't really do like this kind of algorithms quite easily. Yeah, your state itself will be hard to express. Okay, so this is the pictorial view of it. So if you look at it, how it does it is from the start. Okay, you have something from your memory card, right? You select a state probabilistically based on the some criteria like high score and then low visit count. Then you choose maybe a state, then you reload that state from the memory card. You go to that state. Okay, so you can either restore it or you run some goal condition policy, which means that if you use a policy network, if you use a policy-based algorithm, you can condition to this state and you try to reach this state. So this is a way to reach this state without like cheating. Okay, so you either load or you go there. And then after you go there, you explore from there. So then you take some steps, and then whatever you see in your environment, okay, what you do is you map into cells. Okay, these cells are like the abstract representation of your states. So after that, you update the archive with the new states that you have encountered, and then you repeat this process again. So this is essentially go explore. So go is to go to the state, explore is to explore from the state. Very, very simple algorithm. And then you update the archive and go on like that. So the next part here is the robustification phase, which basically maps whatever you learn, the best trajectory into a neural network. Okay. So let's see in detail how this is done. Okay, so take note of all this. Okay, I think we can have some interesting discussion later about how this works. Okay, but before we move on, we need to ask ourselves, is it possible for this to be done on an image? Okay, because an image is supposedly intractable. Okay, there's 255 pixels, right? 255 intensity for red, green, and blue for each pixel. There's like 100 by 100 or 80 by 80 pixels. That's like 255 times 255 times 255. Then you take the whole thing to the power of 80 times 80. So that's like very, very large. Isn't the state space super huge for images? Yes, that's why we use a neural network to do it. Okay, but even neural networks may not get this thing done well. Okay, how do we then make the state space small enough so that we can apply this go explore method? So in the paper, what they did was they actually did this very crude method. So actually, when I first saw it, I kind of laughed at it. Yeah, but it works. So I cannot say much about it. But you can see what they do. They just take the game state. Oops, they blur it. Okay, which is like downscale. And then after that, what they do, they did average pixel values for each of the squares here. So you can see that this thing here maps to here. So it is quite a lot of things are missing, you see. So like where the player is and everything. But apparently this kind of works. So you see the ladder is gone already. So if you ask like a human to play this, I think it's quite hard for a human to understand what's going on. But I think for the computer wise, I can treat this like some form of hashing, where you hash like similar states together. So apparently this method of like hashing kind of works. So this is a way to aggressively downsample and pull, and it sort of manages to restrict the image into a very pixelated image of 11 by 11 8 with only 8 possible intensities. So it's only grayscale. So that's really cool because such a very wide state space over here, a very large state space, can be reduced into this small little state space and it still works. So that also means that Atari games, maybe the way the AI plays the Atari games is very different from how humans play. Because as a human, you kind of need to know where the enemy is, right? Where the human is. But apparently this works already. So maybe a bunch of zeros and ones AI can play already. So yeah, it's a very nice method to reduce the state space. Just, I think we are still lacking something for AI. We are still lacking something that humans have that can make us understand the game better. And that is not represented inside this image. Okay, but it's a good starting point because this algorithm is the state of the art, right? And this is basically pretty much like hashing, and you have to hope that all states are not encoded for, because actually if you have all possible states encoded for, this actually gives you, let me draw out the equation. So you have 8 possible pixel intensities, that's 8 per position to the power of 11 times 8. So if you were to count out 8 to the power of 11 times 8, this is a super large number, which is also intractable if you were to use a tabular method to do it. Okay, but a lot of the state space is not touched. Okay, that's why when they did this method, the buffer did not explode. So that's something to note. Okay, so how do we choose a cell for exploration? So you remember after we do the exploration, at the first step of go explore, we need to choose a cell to go to, right? So if, let's say we haven't explored anything, very simple, the first cell they explore will be the start state. But after you explore one round, what cell should we explore next? Okay, what we can do is we can first, the naive method will be to just use a uniform random sampling, where we sample in our like archive or in our cell states, in the memory of the cell states, and then we just choose one cell to start exploring. Okay, but a smarter way to do it will be to use some heuristics and then choose certain cells that have been explored fewer times and has higher progress in environment. This can be like through score, trajectory length, and so on. Or you can use domain heuristics. Domain heuristics, like for Montezuma Revenge, is like, what are the keys collected? What's my level? And so on. So with domain heuristics, it can learn very, very well. Okay, and then you can choose two ways to do that. In the original Go Explore paper, they teleported there, which basically means you load that state itself. Or you can use a policy, Go condition policy like PPO. You condition on going to that cell and then you go there. Okay, but there's a problem with this. Okay, if you use Go condition policy, okay, you may not be able to get there. Okay, why? Because of the exploration might hinder it. Okay, this is the same as the derailment thing that I was talking about earlier. So if you use a Go condition policy, you may not get there. Just to take note. So Go Explore typically only works, okay, if you can teleport there. So this is one of the limitations of Go Explore. Something I don't quite like because it's a little artificial. I mean, in real life, you can't really teleport to where you are. Right? I mean, if I make a mistake in my real life, I cannot teleport back to that previous time frame and correct it. Okay, I can't really do that. So, but maybe for simulators, you can do it. So that's still an option. So how do we explore after we chose the cell to explore from? How do we explore from there? Very simple. The exploration policy is no-brainer. It's just random actions. Okay, but the random action comes with a super directed random action, because after you choose the first random action, the rest of the actions are very targeted. So it's like if this is the start frame, you just want to explore like this very narrow trajectory. Okay, instead of exploring like all around like that, we want to explore more or less in a very targeted trajectory like that. And I can understand this for Montezuma's Revenge, because Montezuma's Revenge, your character is here. If you like take the action rights, you kind of want it to take action right all the way until the end. I mean, you don't want it to, you imagine if you take random actions, what will happen? You will do this right, left, right, left, right, left, right, left, right, left, right, left, right, left. You will get stuck at the corridor. So this is a very targeted exploration meant for Montezuma's Revenge. Okay. Yep. Or Jet, you want to ask something, is it? Or you want to ask now? I mean, I'm okay to answer now.
No, I think you can carry on with the flow first.
Okay, sure. All right, let's continue. So how do we update this archive? So this updating archive is very useful, actually. This is the one that I found most useful for my own research as well. Okay, because this is a way to try to update optimal trajectories without doing reinforcement learning. Actually, this uses a very, very provably optimal method called Dijkstra's algorithms, where, okay, it's not really entirely Dijkstra, but the idea is similar. Okay, what do they store? Okay, so they store the entire trajectory of the starting state to that particular cell. It is not really then it's Dijkstra. Okay, we store the state of the environment, the cumulative score, okay, which is like the score in the game, and the length of the trajectory. Then when do we update this archive? So we update on two conditions. The first condition is when the agent visits a cell that is not in the archive. Okay, so that's condition 1, which is basically a new cell that you update everything here. Condition 2, okay, your trajectory that you have encountered is better than the trajectory that is stored within this cell here. So what do we do? Oh, there's a typo. So what do we do for this trajectory? We will then, basically, if the trajectory that you have right now, basically your current experience has a higher cumulative score, and it has a lower trajectory length that with the same score, then what we do is we will update the current experience. Okay, we update the current experience and then we will update the buffer. So these two conditions will update the buffer. And then once we update the buffer, in order to encourage exploration there, what we do is we will then reset the information about the visit count for the cell selection. So when we reset the information regarding the visit count, this will encourage the cell to be selected because the number of times it's visited is very low. And this means that this cell can be something good. It will be more prioritized in the cell selection stage. So now let me give you an example of how this Go Explore works like maybe for this grid. So suppose you want to from A and go to B, go to G. So let's suppose there's only one reward. The reward is 1 at the end and 0 all the way. So firstly, I'll do like random exploration. I go here. Then over here, my trajectory is like A, B. Okay, because I start from A, I go to B. Okay, and then actually the trajectory actually is actually not the state. Sorry, I shouldn't write the state here. The trajectory is actually the action here. So maybe we just call this action. We call this action A, action B, action C, D, E, F, G, H. So the trajectory is actually the edges that you transit. So like from A to B, my trajectory is A, and then my score is 0, so I'm not going to write that. And the trajectory length is 1. Okay, then suppose I visit here now. So now this will store AC. Trajectory length will be 2. And then now I go here. Now the trajectory will be ACE of length 3. Okay, and I store this because this is the first time I encounter it. Then I go here. This will be ACEF. And this one will be of length 4. And then finally, I will go here. ACEFG. And this is of length 5. And this one is of reward 1 also. So if I were to, based on the cell selection, I can actually then select like this cell next. Okay, but this is the goal, so I won't select this. But because this has a high reward, and this is like the most explored cell, so the higher chance of selecting that to continue to explore. So let's suppose we have a different trajectory. Instead of going down here, we go by up here instead. So like that. So A1 is correct. Okay, so we don't update it. And we go here. The trajectory is AD with length 2. And then I come here. The trajectory is ADH with length 3. So you see a trajectory with the same reward 1, but has a lower trajectory length. What this will do is we'll replace this one, and then we'll store this into the new memory buffer. And then we'll reset the visit counts to this so that we will select this more in the next exploration stage, in the next cell selection stage. So we can keep doing like visits across this entire thing. Okay, so over here, like we need not even start from the start state. Okay, depending on what you choose. So maybe the next cell I explore from, maybe I start from here, then I explore, continue exploring, and so on. Maybe I can even explore backwards like that. But what will happen if I explore backwards? I'll get A, D, D with a trajectory of 3. So is this ADD greater? Is it better than this? It's not. Okay, so we won't update it. So essentially, when this happens and then you continue exploring like that, you won't update anything at all because the trajectory is worse than all these stored trajectories. So this is something that makes it optimal because you can do this kind of random exploration, but you will update the most optimal trajectories only. Eventually, when you look at your goal state, this trajectory that you look at in the end here, this is the most optimal you have found so far in all your exploration runs. And it's very efficient, okay, because in the traditional reinforcement learning approach, you will take forever to update from the end state to the start state. Okay, because every time you do a Bellman update, you only update from one cell to another cell, one-step update. So imagine you have like 100 nodes, you need to update 100 times, then you can go to the start. So this is way more efficient because you just run one time, you can update all the way to the goal cell already. Okay, I actually did a modification to that method. I made it even more efficient. Okay, so instead of just only directly going to the trajectory that you are visiting, okay, what I did when I implemented the algorithm was that I actually went to the node that I'm visiting, and then I simulate, okay, all the possible scenarios that could happen, all the possible actions, and then I update all these next few states if it's better than what they have inside. So it's like you go to every single cell, you explore everything. So that only works if you have small number of actions. But I find that doing this makes the algorithm converge faster. Yeah, so this improvement that I did myself. I think this algorithm in general is quite efficient. It's way more efficient than reinforcement learning methods using the reward-based signals, which speaks quite a lot about Markov decision processes being rather inefficient. So you can see a lot of modern RL nowadays, we're trying to move away from Markov decision processes. You take decision transformers, for example, you are trying to backpropagate the reward signal more than one time step using transformers, doing credit assignment across the entire trajectory. So I think increasingly we will see such methods in reinforcement learning because it is much more efficient to do the reward updates. Okay, let's move on. Any questions so far for this? Okay, so the next phase, let me just touch on this. We're going to end soon. So the next phase is called Robustify. So in the earlier phase, okay, we typically reduce the difficulty of the problem. We only do deterministic transitions. That's why we can do stuff like this. Okay, if we have stochastic transitions, we cannot really use Go Explore to learn because the state that it goes to may be different. Okay, it may not be consistent. So what we can do is we can then do the Robustify in order to transform whatever we learn in the deterministic case to a stochastic case using a neural network. Okay, how do we do this? We just take the optimal trajectory or the trajectories, optimal trajectory or trajectories from the start to the goal state. Okay, so let's say suppose this is the goal state and this is the start state. Okay, what we'll do is we will start from here. We'll start from one state before the goal state. Okay, and then we will learn the actions that the expert trajectory took from the start to the goal state. So the neural network will take this image here. Let's call this I. It will take the image I or the state itself and then goes through a neural network, and then hopefully the network predicts the probability of an action given the state. Okay, hopefully this network gives you the action that is predicted by this expert. Okay, and this expert can be humans, but in this case, the expert is actually based on the Go Explore phase 1, where we take like the shortest trajectories that we have found in our exploration phase. Okay, so you can actually store the list of trajectories that you have for your goal state, and then we can use more than one trajectory to learn the Robustify phase. So after we have learned until we can reliably obtain the reward for one step away from the goal, then we'll go one more step behind, and then we can start from the next state. In this case, this is the start state already. You start from the start state and you try to predict the actions, okay? From the start state, predict this action and this action to the goal state. So basically, this is like curriculum learning. You start learning the shorter path first, and then once this path is learned, then you learn the longer path, and so on until you can learn from the start to the end. So this is something interesting. So this actually takes quite a long time to train, by the way, because of the way that it trains. But it's better because if we were to start off end to end like this straight away, this purple one, if we were to start off end to end, we may not even learn the right policy because it can just be too complicated. So this actually, by breaking it down into small little steps, it actually helps the policy learn better. All right, so that's it for the presentation. I hope that was interesting. So I give a list of discussion questions that we can discuss. So maybe I just go through them before I talk about it. So like, firstly, how can we simplify the state representation for any environment? Okay, because the environment itself may be complicated. Okay, but we may not be able to like aggressively downscale that much as compared to Montezuma Revenge, where we can just go by the average intensity of the pixels. The second question is like, is there a way that this state representation can match better like how human cognition does it? So I put this question, is it the same as how human cognition works? Okay, I suppose the answer is no, because I don't think like that. In that blobs of pixels, I don't play a game like that. Okay, so what exactly is needed, we can discuss. And then how can we get to a good state without teleporting, without cheating in some sense? Okay, so the paper did offer some views using the policy, basically the goal condition policy to get back. But even then, you may not get back. So how can we ensure this? Okay, next, instead of using this intrinsic motivation for exploration, what if we just use like goal-directed reward, some rewards to guide you to the goal? Something like some compass to guide you to the rough direction. So this is my research actually. I'm doing something like that, a goal-directed reward that never changes. Okay, and the last one is instead of using like a neural network to like learn the actions, maybe can we instead maybe use a transformer to learn the trajectories that were generated by Go Explore? So maybe the decision transformer or just a transformer like in Gato, maybe that could already help to encompass all the decisions that we need, okay, to make. So we learn from the expert trajectories, and then using the transformer, we can like sort of generalize to arbitrary states. Okay, and that's it for today. Yeah, thanks. Shall we have like a question discussion session now? Yeah. So yeah, y'all can ask anything now, or we can do the discussion now.
Hey John, thanks so much for your presentation. I just wanted to ask, right, when you mentioned goal-directed, in the next slide, the goal-directed reward, right? What do you mean by?
Oh yeah, so it's like the A-star search, right?
Yeah.
So for example, in A-star search, you want to, sorry, my diagram, you want to start from a start state to a goal state. So a goal-directed reward can be like a heuristic to tell you how far it is
I see.
from this place to the start state, to the goal state.
Like an informed search, like you have some.
Yes, it's a heuristic guided search. So instead of like maybe doing randomly, you prioritize actions that are closer to the goal more. And the closeness can be like Euclidean distance or Manhattan distance, depending on the problem.
I see. That's interesting.
Yeah, and I found that actually I have some results already. I found that actually this helps with exploration a lot more. You will basically search the state faster if your heuristic is correct. If your heuristic is wrong, you might search longer, but eventually I have some tips and tricks also to ensure that you will still search the state space. Yeah, so that one I'll talk more about it 2 weeks later.
On a related note, right? So this is a question that I saw in the chat. So I noticed that most exploration methods only explore the state space, right? And they ignore the reward. This is probably because exploration methods are probably most needed in those cases where reward is sparse in the first place. However, I would think that exploring the reward function should actually be important as well, especially since we can change the task simply by changing the reward function while keeping everything else, the state space or transition dynamics, all of this the same. So do you think that exploration methods should consider the reward function as well? Like maybe the reward function isn't that sparse, then we could consider it.
But in this case, if you were to explore by reward, how do you explore by reward when you don't know what states lead to that reward? So you will still need something to bias yourself to choose to choose the actions or the next states first, right? Then the reward is the end result.
Yeah. As in like alongside exploring the state space, we also explore the state space plus the reward function.
I mean, if you can sort of find a way to explore different areas of the reward function, then okay. But the most difficult thing is like it's hard to tell what rewards you get in advance, which is the main gripe I have. If you want to use this kind of reward-based exploration.
What do you mean? What do you mean by that? Like,
I mean, let's say I want to explore rewards, right? So I want to say that, I want to try to get a reward. Let's say the reward is from 0 to 5 in this environment.
Yeah.
So you say I want to explore the reward. Then I want to make sure that I get reward 0, reward 1, reward 2, reward 3, reward 4, reward 5 evenly. But the thing is, how do you know what trajectories lead to these rewards? Or you mean the reward function is not the extrinsic reward, is it? Is it another kind of self-defined reward function?
No, just like, and your standard
It's the
environment.
environment reward, right? So the environment reward is hard to explore the value of the environment reward because it is really determined by the state transitions.
Yeah.
Yeah, so it is hard to go like the inverted RL, like upside down RL, where you condition on a reward and try to get a path. That's actually not really an easy problem. Yeah, the reason why upside down reward RL might work, maybe because they actually have a lot of simulations, lots of trajectories. That's why they can learn from it. But without the trajectories, there's no way. Let's say I give you a new environment. Okay, there's no way you will know. Let's say I tell you are the agent. Okay, you are to explore the maze and get a reward of 1, which means you find the goal. So I mean, sure, you can tell the agent, yes, I want you to find the goal, but the agent may not be able to find the goal. Yeah, there needs to be something to like sort of guide it to the goal. If not, it will have difficulties.
Yeah.
Yeah. So I don't think it's quite feasible. I mean, I'm willing to be corrected, but the thing is you don't even know what transitions give you what rewards. So it's hard to explore the reward space. But whereas if you use like intrinsic motivation for curiosity or what, at least you know whether a state is novel or not. So you can bias your search space there.
Yeah. I guess. Yeah. Also, I was thinking like maybe even the reward can be considered as part, like, just a simple variable in the state space as well. And
Definitely. No, so actually, I'm actually against extrinsic rewards nowadays. I mean, after Yan LeCun wrote, I've been right. I asked him in his new autonomous agents paper. I asked him like, so agent, how does it encompass the environment reward? And he said that it doesn't. It just uses intrinsic rewards, and that's why I got interested in intrinsic rewards. I feel like if we were to just use the environment-based rewards alone, okay, it can make the exploration problem difficult. Okay, because of sparse reward cases like this, you will take forever to find the environment reward and end up you may not even learn anything from it. Yeah, because reinforcement learning agents, they all really operate by reward right now. So if let's say this is your agent here, and then you search around and all of these are reward 0, then the algorithm will not be able to like sort of prioritize any direction of search. So it may not be able to reach the goal at the end, because if everything is of reward 0, nothing gets searched. Okay, I mean you will get this radius here and you won't really burst through that radius. Okay, I mean the Go Explore is unique because if a reward of 0, the Go Explore can actually still learn, because Go Explore has another parameter called trajectory length. So the Go Explore will actually learn such that you will find those cases with the shortest trajectory length, and then you will explore from there. Yeah, so Go Explore even with 0 reward, you are still able to sort of optimize your trajectory such that you will get like the short trajectories and focus on that. So that's the beauty of having some sort of like memory-based updates to your states, so that you can cater in the like information such as reward, trajectory lengths. So if you don't want to use like the Go Explore memory buffer way to do it, what you can do is you can do like this thing called the like maybe length-based penalty. So for example, in a maze, in order to get the goal, every time step you don't get the goal, you -1. Once you reach the goal, it's a 0. So it will incentivize people to try to reach the goal, right? Because every time step you -1. Or if you do a discounting of the future time step, like the gamma factor in your reward, you do a discounting, you don't need this minus time step. You can just do a goal time step of 1 and then the rest of 0. But you need to hit this goal. Yeah, so that's the problem. If you have all 0 rewards, your discount factor is useless, because you cannot discount future rewards when your future rewards are 0. Yeah, so in this case, you might need to give like a time step -1 reward, so that you bias the agent to like find shorter paths. Yeah, so in some sense, the Go Explore method sorts of does this kind of biasing. explicitly using the way we update the memory. Yeah, which I find quite cool because I find that if you were to use this kind of reward-based methods to learn, it can take very long to backpropagate the right trajectories all the way to the start. So it might be better to just use the memory approach to do it. Okay, sorry if you was it clear? I mean, I glossed out a lot of details, but yeah. How about the rest? Goku, Evan, do you have anything you want to ask?
No.
Okay, so maybe we just go through like one by one these questions because I think it's interesting. Like, so how can we represent the state representation for any environment? Okay, because earlier on what we saw is that we actually aggressively downscale. We make them into like this kind of pixel grids. But what if the state is like not in pixels and so on? How can we make sure that we can still do an arbitrary environment representation? Okay, and any thoughts? Like, how can we aggressively like make the state space smaller?
You can probably just use an encoder, right, and then represent a smaller dimensional state space.
Yeah. So actually, I was thinking that you can take like a few random trajectories, and then you get all your observations here, and then you can try to like sort of form some form of clustering. So that we can try to cluster them into different groups. And you do some form of clustering algorithm, which I mean, you can probably like maybe do PCA, LDA, that kind, and then you try to cluster them into different groups. Yeah, based on what you encountered. Yeah, but one thing about this is that if you were to use like this kind of encoder to encode your states, okay, when you store them in the memory, okay, whatever you use, like this PCA, LDA, principal component analysis, or latent search analysis, all this you will have to stick to the same representation all the way for the rest of the game. Okay, because the way you represent your state must be consistent in your memory. So if you want to change the way you represent your state halfway, okay, you need to update all your cells in your memory again. I mean, which is possible, it's just that it's not very flexible. So I suspect in like the human mind, we store our state in a very fixed way. And the very fixed way is already based a lot on location. So grid cells, place cells will play a huge part in determining what kind of state it is. And I believe this is already prefixed, like the way we simplify our state representation. And yeah, so one way is to do like this kind of clustering based on the environment samples itself. Okay, the other way, which was used by the paper, which I think is a cheating way, they actually just did grid search of the hyperparameters and then take what works best. So this is a little cheating because you actually predefine your hyperparameters for each game. So Pitfall got one parameter, Montezuma's Revenge another parameter, and you play another Atari game with a different hyperparameter for the state representation. So Jet, you recently sent me a paper on the latent cell representation for Go Explore. So I took a read at that. That is using kind of distribution analysis, something like this, to try to form the clustering. But their clustering can change mid-game. It was quite complicated. But there's some papers trying to work on how to get this state representation, because actually this state representation, I believe, is the key to why they can do so well in Montezuma's Revenge. If you use their state representation and you like pass it to another algorithm, like maybe I don't know, DDPG or Mu0 or Agent 57, I think they will actually do better than the scores reported in the paper, because the original image space is quite complex, but the one that they downscaled and did the grayscaling, the state space is much smaller. So this is an open question. This is quite an interesting question because we need to somehow fix this state representation in order to use the Go Explore algorithm so that the state space can be small enough for the memory buffer to store everything. Yeah, and I believe that this state representation should be a heuristic, should be already pre-built in the algorithm. So I'm thinking more of, I think what they did is more or less okay, like trying to like classify the grid. Okay, but kind of other approaches maybe is to use an encoder mapping, and maybe neural network or something to reduce the state space, or you could do some form of dimensional reduction techniques, like PCA, LDA kind of thing. Yeah. So actually PCA, LDA is not really clustering, it's dimension reduction. But in some sense, you can treat it as like clustering, because like it tries to group the more similar ones together. Yeah.
Actually, right, I have a follow. I was thinking of this about this question. I had a follow-up question, right? So this state, we have been focusing on state representation for the task of exploration, right? Do you think that the state representation, how would the state representation for exploration be possibly different from state representation for RL, let's say? Do you think the state representation of that same environment would be the same both for exploration and for exploitation?
So for exploration, I think the state representation should be something that be as simple as possible, because you don't want to store too many details, I guess. And I guess you want to give some room for generalization so they can use like previous states and infer from there. But if you want to like sort of exploit in the environment, you should use a more detailed representation, because you want to make sure that you get all the details there and get the best action for that detail, for the details. So again, it depends on, I believe RL, or rather in the way that we are trying to get methods to work, I think there's two ways. One is very optimal and one is not that optimal but good enough. So the not that optimal but good enough describes a lot like humans, because we make fast decisions. Our brains are not as good as computers. We don't have that much compute power, so we just settle with what can let us survive. Optimal is like if you have enough crunch time, you use the computer and find the optimal solution. So I think your question of how to represent the state space falls into this category. So if you want to get a very, very good way of doing things, you will need like sort of an optimal solution, which means that your state space should ideally be as detailed as possible to capture the relevant information. Like for a Go board, you don't want to omit one piece, because that will spell tragedy. Okay, because one piece can affect a lot of things in the board. Okay, but for most problems like navigation, you omit like one pixel in your road, or you omit, I don't know, one lane marker. You won't actually cause much trouble in the overall navigation, because there's other things that you can look out for. So yeah, the state representation can be more lenient if you're not going for optimality. Like if you don't want the car to stick right at the center of the road, you can remove the lane markers, no problem. It can still travel, but it might be crossing the lanes. It's still fine, because it still reaches the goal. But if you want like a super good policy that can like follow the lane and stuff like that, you need all the state to be like detailed. So the state representation, rather than, maybe let's not talk about exploit, but we talk about the kind of outcomes we want to achieve. If you want to achieve an optimal outcome, I think we will need a very detailed state representation. But if you want to achieve an outcome that is good enough, then you can use a more coarse state representation. Yeah, and in this case, the Montezuma revenge, I think the coarse representation made it more or less a good enough kind of approach, but it's still better than all other state of the art, because it's just too hard to optimize. So the good enough method actually works out fine. Yeah. I don't know. Do you agree with what I said?
Yeah. I think it makes sense.
Yeah. In fact, I also have some ideas about how to incorporate memory into like this kind of learning. And I believe the way why humans generalize so well is because we have poor memory. Okay, I mean, that might be shooting ourselves in the foot, but it's because of poor memory, we are forced to like associate more scenarios together. Like if I'm late for work, I associate that to be like late for class, late for outing, late for this. I mean, if my memory is very good, I will have stored separate buffers, late for this, late for that, late for that. Then I can reference each context separately. But because my memory is not that great, so all this can be lumped into one category called late. Yeah. So like trees also, you can have palm trees, like the one in my background, the palm tree. You can have like coniferous trees. You can have I don't know, rainforest trees. And then all these are lumped under trees for us because we just don't remember all the patterns of the leaves and everything. Yeah. So next time when you see a tree, you can generalize like what you learned from the other tree because all trees look the same to you. So somehow, if you want to generalize better with fewer examples, you just need to have poorer memory, poorer resolution of what you remember. So more scenarios can fit your memory. So if your state representation is very coarse, more scenarios can fit your coarse representation. You can then learn from that coarse representation more as compared to a very, very detailed one. Yeah. Maybe another example is like this. Let's say if I were to have, like let's say a very detailed memory of like a car. So I remember exactly the car, like maybe I use a Toyota car, I drive a Toyota car. So I remember that the car is like silver key. And then everything else about the car is the same, just that maybe the car in my memory is a red color car with a silver key. Then if I were to change the color of a key to like a black key, then the red color Toyota car with a black key can be a different kind of experience. Then I cannot reference the same memory as the red car with the silver key. So, but the thing is fundamentally they are the same car and the same key. So I can actually use the same memory. It's just that if you were to store even the color of the car in your memory, then these two will be different memory spaces. And then you cannot use that memory to solve it. So somehow memory, I think, is linked to generalization as well. The worse your memory, the better you will generalize. And also maybe your worse the performance you get as well. Because you can't get optimal performance if you miss out certain details, if those details are important for the performance. Yeah. Okay. Yeah. Thanks, Jet. No problem. I'll see you next time. You need to go off already, right? Yeah. All right. So yeah, that's more or less it for the state space and the generalization part. Yeah. So yeah, I don't really agree with this part here, how human connection works. But I believe one way we can do is we can make this state representation, take into account like where the person is, where the enemy is, what's the movement. Yeah, so all this could be inside the state representation as well, which with domain knowledge, actually, they actually encoded these two. But maybe the movement also can be encoded. So that's something else that can be done because for the human mind, I think that's more relevant when you play a game. You need to know how the objects move. Yeah. And how can we get back to this previously good state without teleporting? I think there's no good way. So we maybe cannot force yourself to get back to this state, but we can just try to get to somewhere in the vicinity. Okay, then we can use like goal condition methods to get there. Yeah. Okay, I think that's more or less for the session today. Thanks for joining, and I'll see you all again 2 weeks later. Okay, bye.